All right, folks, let's go ahead and let's get the afternoon session started here. I appreciate you folks hanging in there. I know that it's a lot to ask you to attend two lectures, but got to try to cover more territory with the time that we have left. And instead of doing all 40 minutes at once, I figured, if we keep doing this 20-minute sessions per period, per half day, once in the morning, once in the afternoon, hopefully you can get more, we can cover more territory without totally wearing you out. So, we're almost done, folks. We're almost done. Next week is the exams. So let's power through these lectures and then take a breath afterwards. Okay. I apologize for yesterday. The video, I'm not quite sure what happened. The video cut short at the end, so I want to continue with where we left off there. Okay, I was finishing up my discussion, our discussion of homonuclear diatomic molecules. Hopefully, you got a chance to understand how we can obtain molecular orbital diagrams, determine then electron configurations for different homonuclear diatomic molecules. Homonuclear diatomic molecules being then molecules that are made up of two or more atoms that are the same. Okay, but not all and most of the bonds that we talk about when we deal with molecules are made up of atoms that are not the same. What we refer to as heteronuclear bonding. Okay? So what we want to do then is we want to examine them. How can we determine the energetics of heteronuclear interactions? That is, interactions between atoms that are not the same. And so to do that, then we're going to go ahead and apply the same concepts that we used to examine homonuclear diatomic molecules to examining heteronuclear diatomic molecules. And these heteronuclear diatomic molecules, as the name implies them, are molecules that are diatomic in nature, two atoms that are different from one another. And so, like I said, this particular analysis would be closer to what we would have to worry about with actual molecules, with molecules that are made up of more than one atom, because then most of these molecules are made up of atoms when they are joined together that are not the same. Okay, so let's go ahead then and let's take a look at an example here of nitrogen monoxide. Okay, so nitrogen monoxide is an example of a molecule that's made up of two atoms that are pretty close together. Okay, so close together. And so we're going to take a look at the heteronuclear cases first by examining atoms that are close to each other. So we're going to take a look at nitrogen and oxygen. So let's take a look at nitrogen monoxide first. Okay, we'll examine. This is the molecular orbital diagram for nitrogen monoxide. We can go ahead and write out the electron configuration for nitrogen monoxide. Then it's going to be sigma 2s 2 sigma 2s star 2. Okay. Pi 2p 4 sigma 2p 2p and that should be a 4 right there, sorry, 2, and then pi 2p star 1. Okay, so 2, 4, 2, 4, 6, 10, 11. Okay, so for nitrogen monoxide, then hopefully you recognize them for nitrogen monoxide. We're dealing with a molecule that has 11 electrons. Okay, 5 from nitrogen, 5 valence electrons from nitrogen, 6 from valence electrons from oxygen. So it gives us a total of 11 electrons we have to account for. And if you notice at the energy diagram here, we have the 2, 4, 6, 8, 10, 11 electrons there. And our electron configuration here, we have 2, 4, 8, 10, 11 electrons there. Okay, so this is the electron configuration for nitrogen monoxide. Okay. And the molecular orbital diagram, molecular orbital model does a pretty good job of explaining the energetics of this lone electron here. Remember with the localized electron model, the LE model, it had a hard time dealing with odd numbered electrons for a molecule. The molecular orbital theory does a pretty good job of explaining then that odd electron there. Okay, so then we expect this particular molecule then to be paramagnetic. It has an unpaired electron here. Okay, and so if you notice here, let's take a look at what we have here. If you notice here, we have written out this electron configuration. We have written out this electron configuration using the molecular orbital diagram for nitrogen and not for oxygen. Remember, for the lighter group 2 elements. Remember, we saw then with boron, carbon, boron, carbon, and nitrogen, we saw then that they had a molecular orbital diagram in which the sigma 2p is switched places with pi 2p. The pi 2p is going to be lower in energy. Then we saw then with oxygen and the halogens that they revert backwards. Okay? So the question here then is why then, and so let's go ahead and so this is the actual electron configuration because we can support this with photoelectron spectroscopy. Both of these here, so you'll notice then that this will be paramagnetic, and when I give you the alternative molecular orbital diagram for nitrogen monoxide, you'll see that it will also indicate that NO is going to be paramagnetic. We also have here then, if we solve for the bond order, if you go ahead and do this, the bond order for this particular molecule, let's go ahead and do this here. You got 2, 4, 6, 8 electrons that are bonding. We have then 2, 3 electrons that are non-bonding, and so therefore we'll have a bond order of 2.5. Okay? So bond order for 2.5 for both of these here. Okay. So with that said, then let's go ahead then and let's take a look at the alternative. So this is the electron configuration that we see here, and we will be able to support this with photoelectron spectroscopy. But let's go ahead then and let's take a look at what the alternative could be. Okay. Sorry. So the alternative here, and let me go ahead and erase this here. Okay, so there's the alternative. Okay, so this would be the alternative to nitrogen monoxide here. So let's go ahead and take a look at this here. So we have our 2, 4, 6, 8, 10, 11. And if you notice here, we've switched around. So if you take a look at these two here, so taking a look at these 6 electrons here, they're the 6 electrons that we're going to examine. We're going to examine these 6 electrons here and these 6 electrons here. If you notice then, this is the molecular orbital diagram for oxygen. Okay? This is the way that nitrogen sets itself up. So when nitrogen and oxygen together come together, the choice then for us then is, do the 11 electrons line up in this manner here with these 2 electrons, with the sigma 2p electrons falling below the pi 2p, or does it follow this pattern here where the pi 2p electrons fall below the sigma 2p? Well, again, we already said that this is the electron configuration for nitrogen monoxide. The question then is, why would that be the case? Okay? Well, the first of all, I mean, I think one way that you can imagine this then is that in this particular setup here, in this particular setup where the electrons assume the configuration, they take the molecular orbital diagram of nitrogen rather than oxygen, we place 4 electrons in a lower energy state than here. Here, we have 4 electrons that are in the higher energy state. And remember, what nature does is nature always wants to strive to achieve the lowest energy levels. Having 4 electrons here higher in energy than here, that would not be as favorable. So in this case here then, in this particular situation, we have 4 electrons lower in energy. Here we have 4 electrons that are higher in energy. And so that's one way that we can explain why nitrogen monoxide takes the electron, the molecular orbital diagram for nitrogen as opposed to oxygen. Okay, so remember, this is what oxygen looks like. This is how oxygen, this is the molecular orbital diagram we use to set up oxygen. This is the molecular orbital diagram that we use to set up nitrogen. Nitrogen monoxide assumes the molecular orbital diagram for nitrogen. Okay. Now, we will have confirmation of this when we do photoelectron spectroscopy, but that's an issue that we have to deal with when we deal with heteronuclear diatomic molecules. Okay, so make sure you keep that in mind as we move forward. Okay, so we have a situation here where we have 2 atoms that are close together, but we also have situations where the atoms are not close together. So how do we deal with the bonding? How does molecular orbital theory deal with bonding when the atoms are not next to each other, when they're not neighboring atoms? Okay, so let's answer that question. But before we do, I would ask you just to do number 9. Take a look at number 9 in your problem set. Be able to write out the electron configurations for those 2 molecules there, which is if you have it in front of you. If you don't, you can refer back to it later. But number 9 in your problem set asks you to predict the bond order and the magnetism, that is whether it's para or diamagnetic, for the NO, for the nitrogen monoxide cation, so NO+, and for the cyanide anion. Okay. So go ahead and do that. If you want to, come by and see me tomorrow, and I'll work that out for you. But since we are really short on time, I'd like to do that on your own, and then come by and see me when you have any if you have questions on how to do that, okay? Or if you want the answers, okay? But let's go ahead and let's talk about then what happens when you have heteronuclear diatomic molecules and the atoms are far apart. Taking here as an example then hydrogen fluoride. Okay? Well then we're going to notice then that first of all what we're going to do with this particular molecule is we're taking s orbital electrons and we're going to blend them together with p orbital electrons and we see what happens there. Okay, so hydrogen only has an electron in the 1s orbital, and fluorine has the one electron that it has electrons available in the 2p orbitals, but it has that one electron that's going to be used for bonding purposes. Okay, and so but that electron is different. It's a 2p electron versus a 1s electron there. Now what we have to consider here then is that fluorine is a much more electronegative atom than hydrogen, which means then it's going to take that one electron in the p orbital, that one electron that's going to involve in p orbital, and that electron is going to be pulled a lot closer to the nucleus. It's going to be pulled a lot closer to the nucleus, and so, and again, that's because fluorine is much more electronegative. And so when we take a look at the diagram, when we start out here then, if we take a look at the diagram here, we have the one electron for the 2p from fluorine, from the 2p orbital for fluorine, much lower in energy because it's more stable. It's more stable, it's going to be much more low in energy. Remember with our energy diagram here, the lower on the energy scale here that the electrons are, the more stable they will be. And the reason why this one electron here is pulled in closer, and the reason why it's lower in energy, because it's pulled in closer. It is more stable and it wants to stay. It doesn't want to leave. Whereas with this one, the electron from the hydrogen atom here, it's going to be slightly higher in energy because remember, hydrogen only has one proton and hydrogen is not a very electronegative atom. So when we do this, then you're going to notice then we'll form these sigma and the sigma star here. Okay, so we have one of the p orbitals from fluorine will blend with the s orbital from hydrogen to form our two molecular orbitals here. So we have a sigma and a sigma star. And if you notice here, the sigma, the bonding molecular orbital is going to be closer in energy to the 2p electron for fluorine, but it is still lower. If it weren't, then the bond would never form. But we have here a lower, but it's only slightly lower to show then that the p orbital, that p electron there for fluorine here is a fairly stable one. Furthermore, what we're going to be able to see from this then is that we know then with these two electrons, when they form, they're going to favor the fluorine side because this is slightly, this is lower in energy, it's more stable. These two energy levels are closer together. These two electrons then will favor then the fluorine side of the bond. Okay, so that, or if you want to think about it, the electrons that will spend more time around the fluorine nucleus than they will around the hydrogen nucleus, which would account and explain then the electronegativity, the greater electronegativity of fluorine, and thus account for then the polarity of that bond. Okay, so if you want to imagine this then, if we're thinking of it in terms of the localized electron model, okay, we already said that with the localized electron model, electrons will favor and they will spend more time on the hydrogen fluorine side of the bond because it's more electronegative, making this bond polar. We can account for the polarity of the bond also using the molecular orbital molecular orbital theory, because we're saying then that here, this energy level here is closer. So the 2p orbital, the 2p orbital is closer in energy to the sigma bonding molecular orbital. And so the electron density, then the electrons will spend more time as it does. It'll spend more time with the fluorine, thus making then that interaction between the two atoms. The electrons will spend more time with the fluorine. Okay. All right. So that's heteronuclear diagrams. Okay. So those are the heteronuclear molecular orbitals. Heteronuclear molecules. And so make sure you review this. I know we spent a lot of time on this, but it's not an easy concept to grasp, and it's very difficult to wrap your mind around. So please make sure you take a look at it. It's very important. It helps us to understand bonding for molecules. Covalent bonding is a difficult concept to understand. I think ionic bonding is pretty straightforward. We were able to deal with that back in chapter 7. And here, the last couple chapters, we've been dealing with covalent bonds. And so this brings to an end our discussion of covalent bonds. Okay, so please make sure you review it. Make sure you come by and get your questions answered. Okay. On the AP exam, I've seen few questions asked directly about where they ask you about these types of molecular orbitals. It doesn't come up often. It does come up. However, an understanding of how these atoms interact, an understanding of the bonding, allows you to understand a whole lot more about how molecules interact, how the molecules behave on a macroscopic level, how the molecules behave when they interact with one another. And that's what I want to get started with chapter 10, hopefully. Just a quick overview of chapter 10 when we get there, hopefully on Friday, and then continue on with that into the weekend. Okay. All right. So with that said, then I want to go ahead and I want to start the discussion on photoelectron spectroscopy. And I really like spectroscopy, folks. I think spectroscopy is wonderful because it allows us to see then all of these, allows us to see, when I say see, I put that in quotes, allows us to take a look at what's happening at the level of the electron and at the level of the atom itself, okay, the atom and the electron themselves. Okay? All right, so spectroscopy is a very powerful tool. We're going to look at one type of spectroscopy, and it's known here as photoelectron spectroscopy. But we have mass spectroscopy, we have NMR, nuclear magnetic resonance spectroscopy, we have IR. These are tools that we use, spectroscopic tools, or tools that we use to examine then at the atomic and at the subatomic level. Now, we don't do this directly. We can't actually visualize these electrons and these atoms directly. But what we do then is we study their energies. And we study their energies in an indirect manner. Now, you'll have plenty of time for most of you folks. For some of you folks who will be going on the chemistry, you'll take organic chemistry, you'll take higher level chemistry, and there you will get a chance to deal with these other spectroscopic techniques. But we introduced photoelectron spectroscopy here because it's a fairly simple technique. It's a fairly simple technique that allows you to, that introduces spectroscopy to you in terms of its energies, and then also allows you to interpret a very simple spectrum. Okay? And so what photoelectron spectroscopy does on its most simple level allows us to determine the energies of electrons. It allows us to determine the energies of electrons in both atoms and in molecules as a whole. And I've been mentioning photoelectron spectroscopy as one piece of evidence that we can use to determine then whether we have achieved the correct molecular orbital, molecular electron configuration or not. Okay, and so here now we get a chance to see what that means. Okay, so I've been referring to photoelectron spectroscopy. We'll get a chance to talk about it now. Okay. Right. The cornerstone of photoelectron spectroscopy then is the examination of kinetic energies. Okay? And remember, kinetic energies are the energies associated with the moving object. Electrons, atoms move. Okay? We talked about kinetic energies in terms of the photoelectric effect. We talked about the photoelectric effect back in chapter when we talked about quantum mechanics and Einstein. And remember back then we saw then that with the photoelectric effect, what we do then is if we can shine a certain frequency of light, of energy onto a piece of metal, if we hit the threshold frequency, that is the minimum amount of energy that's needed, then what happens is the electrons that are on that metal gets pushed out. They get pushed out by the photon of energy that we put in. And when they leave with a certain amount of kinetic energy because they are moving. And that kinetic energy that they leave with is going to be dependent on two things. First of all, where they are located on the atom itself. Okay? And secondly, then how much energy we put in. Okay? So two factors affect that. Photoelectron spectroscopy works essentially in the same way. The concept, the idea behind the theory behind photoelectron spectroscopy is based upon the photoelectric effect. And so if you need to, please go back and review the photoelectric effect because that is very important for us to understand as we move forward with this discussion here. Okay. All right. So what does photoelectron spectroscopy allow us to do? It allows us to determine the energies of the electrons themselves. And if we have that, folks, that's the basis of our electron configurations for not only atoms, but for molecules. And so the electron configurations that we came up with for the molecules, the electron configurations that we learned about way back in first semester chemistry, has a basis in experimental data. And if you've had me before, I've always pointed out. And that basis here is photoelectron spectroscopy. And so this is a machine here that is a photoelectric spectrograph here, machine here that does photoelectron spectroscopy. Okay? And so let's take a look at the inside of that machine and take a look at what actually happens here. Okay? So what happens here then is, let me just point this out to you, a few points here, first of all. Okay? and we won't go to this in too much detail, but you have to have a source here, a source of energy. This is the source of energy or source of photoelectric photon, or source of photons. Okay? Source of photons. Okay? Okay. Now, helium is often used, but you can also use X-rays. X-rays have been used in the past, so they're not as powerful. You can use UV light. UV light also can be used as a source of energy, but you need a source. Okay, so this is the source of photons here. Okay, so you have to have photons. And remember, photons are those packets of energy that will move through. So remember, Einstein proposed in that photons are packets of energy that moves through space. They have mass. Okay, and they have a frequency as well. Okay, they have a mass and they have frequency as characteristics of a frequency of these photons themselves. Okay, all right. So frequency then was designated as the letter F, but then you're going to see then the Greek letter mu then is also going to be used to designate frequency, which is what we'll have. So what that means then is that these photons will have, as they leave here, they will have a certain amount of energy. And remember, that energy that these photons have can be calculated if we know Planck's constant, that we learned back in that, and then we have the frequency here as well. Okay, so with the photons here, they all will have a certain amount of energy. So imagine here we have our photons. Our photons are here. We're going to shoot those photons out. We're going to shoot those photons out right there. And they're going to leave with a certain amount of energy. And we have our sample sitting right here. Okay, so the molecule or the atoms that we want to examine, our sample is going to be injected in through here. Our sample gets injected in through there. Okay, and they're going to meet right here. Okay, so when they meet, a collision occurs. And I'm out of time here, folks, but what I'd like to do is continue this discussion tomorrow, but please take a look at this. The collision occurs, and if the collision is powerful enough, and helium here, and the reason why helium is used nowadays rather than X-rays or UV light, because then with helium here, the wavelength that these helium photons, so these are helium photons. Now, when you energize helium, you get these helium photons. The wavelength for these helium photons is about 58.4 nanometers, okay, which if you calculate for it, will give you an energy. That means the energy of these photons then will be approximately 21, I think it's, let me get the numbers here for you. It's approximately, 21.2. And we measure it in electron volts. You can convert that to joules. There's a conversion we can do for joules here. So the helium photons have these properties to them. That means then these helium photons here, they're being shot out at this right here. At this energy here, helium photons have enough energy to expel when they collide with the atoms here. So in here, at this point here, we have a collision. We have a collision occurring between the helium photons and the sample atoms. Okay, so we will have a collision occurring here. When that collision occurs, the electrons get ejected. The electrons will get ejected because electrons are, but obviously the protons won't do anything. They're stuck in the nucleus. But if the photons hit with enough energy, if they hit with enough energy, they will eject these electrons, just like we saw with the photoelectric effect. Remember, if you hit a piece of metal, if you hit metal with a high enough frequency, or high enough or a long, short enough wavelength, the threshold frequency, if you can hit that, then the electrons get ejected. Okay? And so the electrons at this point then get ejected. These electrons get ejected, and then they move into this chamber here. Where what I want to talk about tomorrow is what happens in this chamber here that allows us now to separate out the different types of electrons and thus get the electron configurations that we come up with, okay, and the peaks that we'll see. Okay? And so we'll continue this discussion tomorrow, folks. Okay? And so please take a look at that. We'll continue with this discussion tomorrow in class, and then we'll continue it second session as well. Okay, so nothing due here, but do take a look at this here and look at your POGIL activity. And tomorrow I'm going to use the POGIL activity in order to continue this discussion. Okay, all right, very good, folks. I will see you tomorrow morning. Okay, have a good rest of your afternoon.